Good afternoon, my name is Kyle Rodricks. We are the Autonomous Underwater Vehicle Image Processing Group. I'm also accompanied by Abe Moore, Tony Mitchell, Seth Stark, sponsor with Dr. Sundermeyer and Brian House, and our advisor is Dr. Paul Andrew. So this is our presentation overview. Essentially, we'll be explaining the engineering decisions and kind of take you through the results of the group. So, UMass Dartmouth School for Marine Science and Technology wanted to integrate an imaging system into their already established autonomous vehicle. The IVER had a couple different types of specifications. It had a front seat and back seat computer. It had a 1 gigahertz dual core processor, 512 megabytes of RAM, and 80 gigabyte data storage, as well as Wi-Fi capabilities when not completely submerged in water, and had an 8 to 10 hours of operating time. Sitting down with our customer, we found a couple different things that were really a necessity to the group. We needed to find and create a suitable camera system. We had to ensure that the system had enough available storage to record the image data. And then we also had to provide an access to the images after the whole mission is through. Abe will now explain the engineering requirements.
For the engineering requirements, first and foremost, our goal was to find or create a camera system. We also were responsible for ensuring that the system had enough available memory to record image data, and then also provide a method where we could take that memory back post-mission. In developing our camera system, power was important. We wanted low power. We wanted our device to be power efficient. So in terms of that, we looked at two common image sensors. One is called the CCD, which is a charged coupled device. Another one is called the SMAST sensor, which is the complementary metal oxide semiconductor sensor. Both of these sensors are used in every image device that you can find, whether it's your phone camera, recording system, whatever may have you. Both of these image sensors both have their pros and cons. The CCD is known to have higher image quality, but its con, it uses a lot more power. As with the CMOS, it's very power efficient, but then again, it takes in a lot of noise. So from that point on, we move on. In terms of choosing our sensor, we also have to be concerned with the ability of a shutter, a global shutter and a rolling shutter. A global shutter is just a reference term of how a sensor takes in the image. A global shutter takes in the image simultaneously, as a rolling shutter takes in the image sequentially, piece by piece. Now, if you look at the slide, we have 3 images. It's of the spinning can. If you look at the left image, it's a spinning can seen by the naked human eye. If you look at the middle image, it's an image taken in from a rolling shutter. And as you see, it's in movement. It's a little clearer from the picture on the left, but not exactly what we're looking for. If you look at the right picture, which is used by the global shutter, you can see how clear it is. And mind you, that can is still moving, but that picture is so clear. And that's exactly what we need. So we end up rolling with the global shutter. As a group, we decided to go with the Mako G24 3C camera. And there's 3 pictures that we've taken using that camera. If you look at the image to the left of it is the biggest image. That's the full resolution of the picture, which is resolution size is 1926 by 1216. If you look at the image on the top right, over here you can see the medium size image, which is the resolution size is 1080 by 720. If you look right under that, that's the smallest resolution that we can take with the picture cropped. The resolution size is 640 by 480. Now cropping obviously is beneficial to us we can take control of our resolution sizes. But also with cropping, as you can see, we lose a lot of field of view, and that's not exactly what we want. So to fix that problem, there's an operation within the camera called information binning. And what information binning allows us to do is to maintain the resolution size by cutting that resolution in half. As you can see, this is our full resolution size image taken by the camera we've chosen. And to the right, this is the binning process at its complete form. The resolution is actually cut in half, but as you can see, it also results in a brighter image.
Hi everyone, I'm Tony. I'm going to take you through our 2 design scales. We didn't just jump into picking a camera and implementing it into the machine. We went through a couple of different preliminary designs, and the first one we had was an independent system, something that was completely unassociated with the AUV's host system. That would entail incorporating a hard drive, a processor, RAM, all of the amenities that would require you to control and operate a camera. Being that we were constrained with space and weight restrictions to maintain the AUV's buoyancy and its already calibrated status, we chose not to go with an independent system because the AUV has all of these components already present. So it has a backseat coin, the backseat driver, which is the processor that controls the processes of whatever instruments you're running, in this case the camera. So we chose to go ultimately with the integrated system because of the lack of space, of the lack of ability to bring in new components to an already restrained system. The overall design of the integrated system was ideal for the reason of not needing these additional components, additional costs, additional weight requirements, temperature changing metrics internally. So without intruding on all of those, we chose to use the full integration, which was ideal. And from that full integration, the main obstacles were communicating and powering the camera. The communication method was ideal for us to do a Ethernet protocol for communication, and with that we were going to also power over Ethernet, which is PoE devices are using a voltage that rides over the Ethernet wire, as well as the data transmission receive signals. So that was a primary option. However, it was a higher power consumption rate using the PoE method. It was a 2.8 watt power consumption to operate the camera. And the alternative to that was using the 12 or 24 volt capability of the camera, which the system had naturally. It was a system that provides a 24 volt output to operate most of its external components. And the main benefit was that it was a 2.4 watt power consumption, which ideal for our system that is going to be deployed on a mission and isn't able to plug into a wall. We want to minimize how much power we're draining from the system so that it can complete its 8-hour workday tour of mapping the underwater, whatever region it's being operated in. So, being said, the 48 volts power over Ethernet is not used, again, because of space constrictions on the internal, the volume of space remaining unused is very small internally. It's pretty much packed to the brim with components that operate the system's autonomy. So as far as technical design, again, the integration for communication, we use the Ethernet protocol. It's not a standard RJ45 Ethernet connector. It's a sub-con that is a watertight polypropylene rubber connector. So it's formed to restrict water entry, and it's not a standard connection, so it's not something you can buy at a local Best Buy, or if Radio Shack still existed. So we resulted in fabricating our own cables for test, and there's specific wiring diagrams that associate the Ethernet Type B connection, and also integrating the camera's power over a high rose connector, which is where we operated the 12 to 24 volt capability of the camera to power. With that, the biggest issue for an 8-hour duration of camera operations, whether it be film or still frames, the storage. So as we're taking in raw data, converting to a compressed file type, whether it be JPEG, there's a storage minimum, or there's a storage maximum of 80 gigs. And depending on the file types, we would fill up that 80 gig space pretty fast, taking high resolution pictures. But that's why there's variants of high, medium, and low resolutions to take in different sizes of the file, and kind of play with what your duration of mission is going to be, and how much space you're going to occupy, and if you're going to run out of space at the end. So the need for an expandable storage was pretty much just solved with the introduction of a USB thumb drive to expand the storage where data would get stored to be retrieved post-mission. And I'm going to pass it to Seth to give us programming.
So in terms of the code design, part of the reason that we got the camera that we did was because it came with a called the Bimba SDK, which included a gigabit Ethernet transport layer control thing and API to control it. So the Bimba API let us set up the camera, open it, configure things, exposure, resolution, pixel offset, binning, all that stuff, and then it would return the image file. And then from there, we used a library called OpenCV, which means Open Computer Vision, which is an extensive library. You can do all sorts of cool stuff, object tracking if you really want to. But we just used it to take the raw pixel data from the Bimba API, run it through a filter, because we have the camera taking images in OGG format, and then writing it to a JPEG file. Just store in the system. And we ended up designing all that in C++, in part because OpenCV is written in C++. We were going to do it in C#, which has a built-in image transform library, but we couldn't because the version of Bimba that runs on the Linux backseat of the actor didn't support C#. So we had to use C++ instead, which is also a language that none of us had ever used before, which So obviously we ran into problems with the code. It took us quite a while to understand the nuances of doing image manipulation digitally inside a computer. There was a lot of concepts about pixel formats and how the image gets transferred from the camera to the computer to a file on the hard disk. Also just understanding how the Ethernet camera works at a basic level, how you have to use the API to control it, and then the signals that you needed to change. Communicating image data between OpenCV and Bimba proved a little more challenging than we'd initially hoped. It had to be debared, which is transferring from one pixel format to another. But once we got that figured out, it was relatively simple to write it to a JPEG file on the hard disk. And then for the code, we wanted to have it be able to continuously take image given the frame rate for a given amount of time. Unfortunately, that means that we needed to have some kind of multi-threading support in order to use interrupts to control writing frames to memory as they're received by the computer. But on the backseat of the iVert, they had not installed it. It's an old OS, so they did not have the latest, which is the only version of C++ that had multi-threading support. So we ran into some problems with compatibility there, and we had to update the GCC copy on it to compile the newer version of C++ to enable that support. And then just making a functional build environment, because we did initially the design of Windows for just ease of use because we all have Windows machines, but then of course we had to make it work on the Ubuntu system, which meant writing a make file and sorting out all of the cross-platform things that didn't really add up, which was challenging.
So as you can see now, this is our test plan. Essentially, we got our test plans from the engineering requirements, and we had to find and create the camera system, ensure the system had enough available storage memory, and then provide the method of accessing it post-mission. Most of these were the find and create. We ended up finding a camera system that we definitely feel is the best camera system for this. We did analysis on the total data that would be necessary, and then to provide the method of post-access, the iVert actually connects to a router that is given by Ocean servers, and you can then remote into the desktop and transfer things off by SSH or FTP protocols. So with the test results, there were requirements that we definitely met. We were able to create that system. We proved that we provided the storage solution by just small USB flash drives, and then the method of transferring off, like I just stated, you can FTP things out. As Seth stated, one of the problems that we did not meet was taking X number of images to create a frame or to create a video. Because of the limited processing capabilities of the backseat, we decided that if we were just able to take individual images and then stitch them together off of the iVert, it'd be the best way to make video. Video isn't the most important situation for the iVert. Actually, taking individual images is our sponsor. So essentially, we were able to kind of really complete the mission. We'd like to be able to offer video, but it's not the biggest necessity. The one thing that we definitely didn't meet, unfortunately, was full autonomy of the vehicle. With this system, it'll be going underwater. There will be no user input. So the biggest problem is we have to find a way to get the user to get the system to take images. There were a couple different ways that we believed that we could do it. The first one that we really believed the best way to do it would be to put it on a continuous timer in a sense. If you wanted to set it for a 5-hour duration, set it for 5 hours, it begins taking images, it'll take an image, say 1 image per second. That way at the end, you'll have X number of images that you can transfer off, and then you'll have that in a file. After that, another option that we believe that would be capable is the iVert is capable of using the remote helm, which is able to send data packets from the front seat of the iVert to the back seat. And you could use those to trigger different types of information, trigger an interrupt, which would then say, take an image. And then you could do that off a GPS location because it has dead reckoning underwater, which then guides it. So if it changed, 5 degrees is a little lot, but 5 degrees in longitude or latitude, it would then trigger an interrupt and then take an image. So in summary, we definitely feel that we found the best option with the camera system that we chose. SMAST will be able to use this camera, whether it's just for this or for another developed situation later on. It's a more than capable camera for years to come. And there were a lot of lessons learned throughout this process. Communicating with our customer was definitely probably the biggest lesson learned. We spent a lot of time researching situations that weren't really necessary. We came up with a whole kind of mock design for waterproof housing where our customer really wasn't interested in us actually providing the waterproofing for the camera system. Instead, he really wanted us to spend all of our time developing the system and just finding good resources necessarily to take images. Another one was identifying requirements that were within the scope. If we had better communication with our customer, we would have known right from the get, the most important parts of the project. We also found that the scheduling, the deadlines, and tracking work hours was something that we really struggled with throughout the process. And had we done that, maybe we would have been able to, progress a little bit further than we ended up with. And then the importance of breaking down the project into a smaller component. At the beginning, we felt really overwhelmed. We just kind of dove in and started finding all of these answers for things that we could do. If we would have been able to break down the project right from the beginning and really figure out what it was that we needed, again, we probably would have been able to get a little bit further and not spend so much time researching and moving forward. So unfortunately, we were getting images prior to this situation, but within transport today, we weren't able to connect to the back seat. Because the only option on this that has connection is the front seat computer. It has the Wi-Fi adapter. So essentially the way to connect to the back seat is to route packets from the back seat to the front seat, which you can then communicate and get information off. As you can see here, we're currently connected to the front seat, but the back seat is just unfortunately not accessible. So we were able to get the code to take an image, and we're just not able to access it right now because of some type of finicky connection between the front and back seat.
We ran into a lot of issues with the compatibility between the Microsoft system and the Linux system. There was a lot of workarounds that were tried to employ, but not all of them were successful.
We were able to get a finished product, so we were able to get images. Any questions?